Good morning, everyone. I'm Manoj, and I'll present our research on LATTICE, an efficient in-memory DNN model versioning library for non-volatile memory expansion devices. I led this project during my PhD at Florida International University, and I would like to thank my co-authors, along with the National Science Foundation, SIGET, and NetApp for supporting this work. Before I dive into the technical discussion of LATTICE, how it works, and why we believe it is great, let me answer why it is important. Why should anyone bother about DNN model versioning? And what is model versioning? Model versioning is essentially the task of persisting model state at different points in time, and then managing these model states for different downstream tasks. Now, this sounds like model checkpointing. What is the difference? The difference is in the motivation. DNN model checkpointing solutions are primarily designed for failure recovery, and that's what these solutions are optimized for. As you can see in the top figure, model checkpointing solutions are only concerned about the latest checkpoint. Once they persist a new checkpoint, they delete the old one to maintain space efficiency. However, different downstream tasks such as online training, model analysis and debugging, adversarial attack prevention, and model lifecycle management needs access to multiple model versions. And there's a need for a low-level model versioning solution that can support these applications. Okay, in the previous slide, I answered why DNN model versioning is worth exploring. But why do we need to do it in memory? There are two main reasons: latency and ease of programming. If we explore existing checkpointing solutions, on one end, we'll find traditional solutions designed for hard disks and SSDs. On the other end, we'd have newer methods that use volatile memory that support recovery from partial cluster failure. These two methods lie in two different ends in the memory storage hierarchy pyramid. On one end, we have low latency and no persistence. On the other end, we have persistence, but at the cost of high latency. The emerging storage class memory and non-volatile memory expansion devices provide a middle ground. These devices provide a mix of both low latency and higher bandwidth. It essentially leads to lower training stalls and more frequent model versioning. This is the primary motivation behind exploring in-memory solutions for DNN model versioning. In addition, the in-memory versioning means ML application developers can now write entire applications using the load-store memory interface instead of juggling between memory and file I/O API. With this, I've now answered the motivation behind in-memory model versioning. Now let's take a look at why existing solutions can be used for efficient model versioning. If we want to enable model versioning for a file I/O-based checkpointing solution, such as CheckFreak, all we need to do is to turn off the old checkpoint deletion function, as you can see in the top figure. However, I have already mentioned that file I/O-based solutions are not the most efficient in terms of latency and frequency. Hence, we need to look at in-memory solutions. Let's start with LibPM, which is a library that offers direct persistence on NVM devices through the memory interface. In LibPM, we can map the neural network on a non-volatile memory device and commit new versions from GPU to NVM through the memory interface. As you can see in the bottom figure, the in-place update requirements of LibPM need to trigger expensive model version creation operations at the beginning of each version creation process, which would increase the snapshot creation time, increase training stalls by blocking the wait update operations. One easy solution to this problem is to pre-allocate the memory pages required for model versions and transparently update the memory pointers to the new version location after each versioning operations so that it fills in place to the application. This is in line with the double buffering technique used by GPM and LightCheck to save time on version creation. And this will reduce the time required for model versioning, as can be seen in the bottom figure. However, such a solution won't be able to exploit data sharing opportunities between model versions and will result in higher memory usage on NVM devices. This can be seen in the figure on the right. In case of LibPM, the memory usage is increasing linearly as memory for new versions are not pre-allocated. However, both the libpm and the double buffering or buffering of GPM or light check is going to end up in the same situation where the space requirement or the space utilization would be very high. So we propose Lattice to address these issues. It is a direct persistence-based in-memory model versioning library designed for emerging non-volatile memory expansion devices. Lattice uses a persistent container-based approach on top of FSDEX interface to expose direct persistence. It exposes a set of streamlined APIs for persistent container management, memory annotations, and version creation and restore. Space optimizations during model versioning happen transparently based on which memory pages were updated between different versions. We follow three overarching design principles to make Lattice efficient. First, we organize the version creation workflow to eliminate version creation operations from the critical path. Next, we implement a scheme to identify data sharing opportunities to create space-efficient versions. And finally, we parallelize memory movement operations to reduce version creation time. I'll give a brief overview of how our design principles translates into action. The model versioning process is a three-stage process: snapshot, persist, and version creation. And Lattice uses a persistent container and in-place update mechanism to support model versioning, which requires we initialize a persistent container at the beginning of training and map the entire neural network in a working copy inside the Lattice persistent container. Whenever a new snapshot operation is triggered, model parameters are updated in place in the working copy. The in-place update mechanism enables Lattice to efficiently track which memory pages are updated since the last version and persist only those pages in place, which is happening in step 5 in the figure. And even if a failure were to happen after this step, we can still recover from the working copy. Once the memory copy is persisted, the model version is persisted, and we can stop right here. If we are thinking only about failure recovery, we can always recover from the working copy. However, this is going to make our next snapshot and version creation expensive. That is because the persisted version needs to be moved to a new memory location before another version can be snapshotted and created in place. Hence, we preemptively create a new version at this point to move version creation operation from the critical path. In this preemptive version creation, we only move the updated memory pages since the last version to keep versions space efficient. And since the preemptive version creation happens at the NVM device level, which does not suffer from bandwidth bottlenecks of PCIe, we can parallelize the memory copy operations to reduce version creation latency, step 10. And this is the gist of how Lattice works and how it provides the benefits. We implemented Lattice on top of FSDEX for NVDIMM-based NVM expansion devices. However, it can easily be modified for CXL-attached NVM devices by modifying the flush and drain API calls. And also, Lattice is written in C, meaning it can be integrated with the backend of most DNN frameworks. In this case, we integrated with DNN framework called .NET. The evaluations were done on top of NVDIMM-based NVM devices using different image classification models. And we retrofitted checkfreaks, asynchronous checkpointing for file IO-based model versioning as a baseline. Since we are short in time, I'll only show the important results here. And please read the paper for more details. So we started our experiments by measuring training stall reduction of Lattice. And in our experiments, Lattice can reduce training stalls due to version creation operations up to 35% when we compared with the checkfreak, as you can see on the left figure highlighted in red. The x-axis are models tested and y-axis is latency. So the lower the better on the y-axis. Next, we look at the benefits of version creation workflow reorganization, which you can see on the right plot. The reorganized version creation workflow of Lattice also reduces overall snapshot delay compared to libpm, as you can see in the right. And it is lower the better on the y-axis, similar to the left figure. Next, we compare Checkfreak and Lattice to measure if it really decreases the snapshot time, persist time, and overall model versioning time or checkpointing time. What we found is Lattice can reduce overall model versioning time up to 72%, as highlighted in the red in the right figure. Y-axis is latency, so lower the better. And for snapshot time and persist time, Lattice also performs better than Checkfreak. And finally, we measure space efficiency or space utilization reduction by Lattice for different workloads. When Lattice cannot find a space optimization opportunities, it uses the same amount of space as Checkfreak. However, when it finds opportunities, it can reduce the space utilization by a significant amount. For example, for VG16 fine-tuning workloads where only the last two layers were tuned, Lattice can reduce the space utilization by up to 92%, as you can see on the right figure, highlighted in red. To conclude, we propose Lattice, a persistent container-based DNN model versioning library, which reduces both versioning time and space utilization when possible. Lattice is orthogonal to existing in-memory checkpointing solutions, and it can support applications beyond DNN training. We'll open source the code on GitHub, so keep an eye on the shared link, and thank you for listening.